everyone. So I'm going to basically give you a rundown on basically cover the fundamentals for path integrals for interacting field theory, however much that was covered in lecture 9. So I'm not going to go over all the details, just I will try to give you a summary. The lecture notes are there that Nafiz Bhai basically provided on the Slack channel. So to start, let's start by looking at the action for a field that is free. So a free field theory, if it had an action, what would it look like? Okay, so the action for a free field theory will look something like this. So this is a functional, and I have the integral over d for x, and I have the kinetic terms, and that's all, right? This is a free potential, and I have the action for a free field theory. But what we would like to do is basically we would like to evaluate the path integrals for an interacting field theory, right? So therefore I write the generating functional which we know we can write as the following expression. And for an interacting field theory, this expands to the integral over the exponential of the action, where now the action is not only complicit of the free field terms but also the interacting terms, right? So let me denote the free field Lagrangian as L0, the interacting Lagrangian as L1, and the extra term J5, which was pre-existing. Okay. So now if we evaluate this generating functional, in that case I break this down in its definition, and what I would get is the following. So keeping the interacting term, the one with the interacting Lagrangian, out with the expression of the generating functional as such, and keep the part with the free field Lagrangian inside, like this, basically separating the two. Okay, so I could say by looking at this expression that this generating functional Zj is proportional to e to the power of I d for x, the interacting Lagrangian, and the generating functional for a free field theory. Okay, so this is the free field result that we know already. So the reasoning to why we write this proportionality is because you cannot say that they are equal per se, because you can have terms and constants in front that would vary when you compute the integrals and so on, and hence you cannot say that they are equal, but you can say that there is a relationship which is proportional to this expression. Okay, so here I can write the expression for the generating functional for a free field as the exponential of I by 2. This is something that we've seen before. Is given as follows. Okay, so from here we can write the free field Lagrangian as well, which comes from the expression of the action, which is pretty simple, and this is minus half the kinetic terms, and also we can write the expression of the propagator, which is given as follows for the free field, and this is something that has been also covered before. So if you want to physically understand what the propagator does, is it basically propagates, right? So if you look at the expression of the propagator, this basically implies that you have the propagation from 2 points, which is x and x prime, and this whole expression is the expression that correlates these 2 points. So this is the propagator that is expressed by this particular expression over here. So now let's take a situation where we have x1, where x1 is complicit of t1, x1, y1, and z1, which are general coordinates. So from here you can compute the correlation function using the generating functional of a free field. So you can write it as the following, which acts on the generating functional z0 at j equals to 0. So over here what we're clearly doing, or what we can understand clearly, is a functional derivative over j, which you see over here, provides a sort of insertion inside the path integral. Okay, so this insertion, basically what it does is we take it so that taking this n functional derivatives, depending on how many x's you have to derive it as many times, and then setting j equals to 0 and normalizing properly gives us this correlation function. So that is exactly what we're doing when we're defining the correlation function as such. So now, if this is the definition, in that case we can also define the correlation function, actually compute the correlation function of phi squared and phi 2, which is phi squared at x1 and phi at x2, in the following way. So this would be complicit of 2 functional derivatives, as you can see. Actually not 2, 3, because I have 2 of these and 1 of these. So I have 1 of this, which is with respect to x2, j2, or you can call it j2 as well, and 1, actually 2 of this one. And this acts on the generating functional for the free field, and we set j equals to 0, which asserts the correlation. Now we can express the free field generating functional in this particular way, which is also very intuitive, and we can express it as e to the power of this diagram. Now let's try to understand what this diagram means. So you see over here that this part basically gives you the propagator, right? And these 2 points is basically given by this, basically this whole expression is given by this expression over here. So what it asserts is that when you have 2 of these, basically when you're running the integral over 2 of these, that means that you have 2 points that you're running the integral over. This propagates between these 2 points, and an exponential over this whole expression basically tells you that there is a propagation from x to x prime. So hence I can write z0j as the exponential of this expression over here, which is given by this mathematical expression written here. So basically what I'm doing is I'm just trying to formulate this using diagrams. Okay. So now if I write this in this context, then I can expand the exponential. This will be 1 plus the first order term. As we know, an exponential expands as what? You have 1, and then you have the power of the exponential, which over here is this expression, which is this diagram over here. And then the third term is basically 1 by 2 factorial square of the power. So over here, since there is 1, I will consider 2 as the square of the power, right? And eventually you will have 3 and so on. So this is essentially the expansion of the exponential. Now let's write this down, which is 1 by I del by del j xi, and we acted on this expression because essentially what we're doing is we want to, you see over here we are actually implying that these terms are acting on the generating functional of z0, right, the free field generating functional. So since we've expanded the exponential like this acting on 1 is basically 0. So therefore the first term that comes out of this is this expression acting on the first term over here, which is the one that I wrote. Okay. So therefore this will equal to now writing the diagram out, x1 from x prime d for x prime, right? Because basically you see that the expression of this diagram is given over here, and since we have functional derivative over jx1, you get the propagator to be x1 minus x prime, and one of these will go away, right, the j's, and I'll be left with this. So now the way we compute this is we set j to 0. So we have one of the j's left. So therefore setting j equals to 0 will make the whole expression 0. Therefore this boils down to 0 as j is equal to 0. Now this comes essentially from the fundamental principle of calculus, right? Because when we derive an integral, we should get whatever we have left. And we basically derive the expression that is inside, and you get 0 because one of the j's survive, and therefore setting j equals to 0 will give you 0. Now we can write this in the following way as well for the other terms. So the other terms that we have, which is the second derivative, this one, is the following. And we acted on the first term of the generating functional again, and what we would get is 2, right? Because now you have two of these acting together, so therefore one of the derivatives will get rid of one of the j's, which is here, and the other derivative will also get rid of the other j that is here. So you're left with the only propagator, and this is what I have left. So this basically comes from the idea of acting a functional derivative over a functional integral as follows, and it should give you the function that is left, right, in the variable that you're computing the derivative with, and so on. Okay, so now what do we do next? We basically set j to 0, but since you see that there is no j left in this expression, this stays as is, and we have only the propagator, which we can write as the correlation function if you see the expression from here, right? And therefore the correlation function over here is just phi x1 x2, because essentially that is what we are computing, right? Okay, so I missed a 1 over here. Okay, so now you can also show for other terms in the similar manner. Let's say if I have the second derivative again, acting on the second term, sorry, not the second term, the third term from here, like this one. This is the third term of the generating functional. So I'm now computing the second derivative on the third term of the expansion essentially. Okay. So you can see that, of course, since you have square of this integral expression, you will have more than 2j's. And that is given. That is pretty imperative. So in that case, you will have some of the j's included. So therefore, I know for a fact that some terms including j will survive, because the derivative will not be able to cancel them out. And hence, once we set this to 0, this will also go to 0. So in that case, you can generalize a formulation for these correlation functions. So let me generalize one for 4 phi's. This would just be I to the power of 4 and 4 functional derivatives over the free field generating functional, and we set it to 0. And this gives you the relationship between the correlation function and the generating functional, and this is called the LSZ reduction formula. Okay, so now let's try to compute this just heuristically over the top. So what you have to do is basically compute the functional derivatives as I've shown over here, right? So each one will act on z naught, right, in the way that z naught is expressed over here. And you will see that we will get propagators like this one. And you will get a set of propagators, in fact, and all the propagators will look something like this. You will get one set where you get the propagator of x1, x2, which is what we got for one of these terms, right? This will be multiplied with another propagator, and I would prefer if you could break this down at some time, because normally these calculations take some time. Once you get the hang of it, it will be much simpler to do. And you will get another set with the product of the propagation as such, and finally one more set, so you will get 3 in total. Which is the following. And since these are propagators, you can decipher them in diagrams. So basically the first term over here, I can write them in the form of the diagram. So since I have x1, x2, x3, x4, so therefore 4 points. So let me denote 4 points over here. And I have the propagation from x1 to x2. So if this is 1, 2, 3, 4, then the first term basically tells me that there is a propagation between x1 and x2 and 3 and 4 as follows, right? Now the second term over here again poses the same x1, x2, x3, x4 points, labeling them as such, but the propagation now is between x1 and x3, so like this, and 2 and 4. Finally, same 4 points, except propagation is between 1 and 4 and 2 and 3. So 1 and 4, 2 and 3. Now remember that this expression is equivalent. It just depicts the propagation from one point to other, so therefore it's the same. Now these diagrams that I've written down over here are called Feynman diagrams, and pretty simple ones, because once we have interactions they will get much complicated. Now let's review the interaction part that Nafis Bhai covered. So now, including interactions, let me write the interaction action. It is given as the following, which is very similar to the one for the free field, except now you will have terms that incorporate interactions. So you see phi 3 is an interaction term with an interaction or coupling constant g, where phi 3 is a self interaction between phi itself, the scalar field. Okay, so now if I write the path integral using this action, I can write this as the exponential of the interacting term and the free term. So separating the two, basically follow the same medicine that we did earlier. Now we will use this particular expression and use the definition as follows, where if I have an n number of functional derivatives acting on the exponential integration like this, you will get phi as many times as the derivative. Okay. Now I can expand this because this is to the power of n, right? And I can expand this in the following way. I can write this just a simple expansion. You will have the interaction terms, sorry, I think I wrote it correctly. So basically you can write this as an expression of the expansion, right? So there is a very nice proof to show this, that any number to the power of n expands the same way as an exponential. So I will expand it in the same way as the exponential term over here. So I can write this as the following. Expand the terms accordingly. This whole thing squared and so on, and this is multiplied with the exponential, in the integration of the exponential of the free term, which is given as follows. So now you can use the definition over here and basically write this expression in terms of phi's, and therefore what you will get is 1 plus minus g by 3 cubed phi and half of minus g by 3 cubed phi cubed squared, and so on. And this is again multiplied with the exponential term for the free field. Okay. So now you see that this looks like a power series as well, and you can recalibrate your exponential because we also know that the exponentials also expand the same way. So I can write this expression as the integration of the exponential of phi, and this is multiplied by the exponential of the free field. So I can write this whole expression in this compact form. Now, I know that if I write this over here, then the exponential of basically the path integral exponential over here can then be written as an amalgamation of the free term and the interacting term, which is a phi 3. So therefore, I can write this as the exponential of this is the exponential of the functional derivative inside the integral as such, right, like before, using the same methods, acting on the free field generating functional. So basically what we're doing again is acting this functional derivative over the generating functional, which we have done before, and the answer that we will get is essentially half times I divided by 3 factorial for x propagator between x minus x and d for x4 j x4. So this is one of the x4s, so one of the terms. You will get many from here. So I want to focus on one of these terms because this is what Nafiz Bhai showed, and also I want to explain where this diagram comes from. So the way you can read this diagram is essentially take in the fact that you have two of these. So therefore that must assert that you have 2 points. So let me write that down. So I have one point x, right, and the other which is x4, and then you have two propagators which are a propagation between x minus x or x to x and a propagation from x to x4. So I know x to x4 will have a propagation in this direction, in this way in particular, and a propagation between x is a self propagation, so it comes back to itself, so there is loop. Okay, and this is how you would read the diagram. So now more on interactions and more on interactions of fermions and how we compute their path integrals, it will be covered by Dr. Nafiz Ishtiaq in his lectures. Okay, so this was what I wanted to basically give you a rundown, a summary of what he did, and sort of follow through with the fundamentals of this lecture. Thank you.